Okay, let's go over the Doppler effect. So this goes on the right side. The Doppler effect is when the pitch of an ambulance is higher as the vehicle moves towards you, but then the pitch drops as it moves away. This is due to more or less wave crests encountered, resulting in a higher or lower frequency. So that's a little hard to understand, but we'll come back to that. Okay. Right now, I'm just gonna show you how to plug in the numbers in our formula, and then we're gonna come back to this. Okay. And what that means. So here you have the formula FD, FS, V. So it looks like a really complicated formula, right? But it's super duper easy. And you're gonna see how simple this is. So this is gonna be the change of frequency due to the distance. This is the frequency of the sound. This is the speed of sound, VV. This is the velocity of the object hearing the sound. And then this is the velocity of the object making the sound. Okay, so let's jump into one example. This goes on the left. Okay, so here you have a guitar player. That should be player. Sounds C above middle C. That's the frequency 523 hertz while traveling in a convertible at 24.6 meters per second. If the car is coming towards you, what frequency would you hear? So the way you answer these problems is, first of all, this right here is supposed to be the frequency of the sound. Okay, that plugs in right there. Now V is going to be the speed of sound. So this is 343 and 343. Look, we're almost done filling in everything right in our formula. Okay. Now VD and VS, this is supposed to be the velocity of whatever's hearing the sound. This is the velocity of what's making the sound. Okay, so let's kind of visualize here of what's going on. So here you have a guitar player, they're in a car and they're traveling. So you're standing here, there's a car passing by, and there's a player here, he's playing a guitar. That is my guitar. And that's my car. And they're traveling. And here you're standing still, right? So you're not moving. So this guy is the one that's making the sound, right? Velocity of what's making the sound. So the guitar player is in a car and they are moving this fast. Okay, velocity of what's making the sound, 24.6. You're not moving here, you're still, right? So that's 0. Okay. So now we do 343 minus 0. 343 minus 24.6. 318.4. So now we are going to divide here, 343 divided by 318.4. And let's just go up to 2 decimal places. I mean, the more numbers that you use, the more accurate this will be, but then don't even round. We'll just use this right here, okay? If we're not in the same page here, let me show you here. So our answer was 0.0772613. I'm just gonna show you something here, but here let's kind of do this first. 523. So 1.07. So I'm just gonna use up to the first 2 decimal spots. Okay, I'm not even gonna round. So now I'm gonna do 523 times 1.07, and then that's gonna give me my new frequency sound, 559. Okay. That's going to be my new sound. Now, if we're not on the same page here, and if we use 343 divided by 318.4. See how it gave me, like, here we're just using the first two numbers. Now if we use all the decimals, it's going to give you a more accurate reading, but just so that we're all together, we're only using the first two numbers, okay? Now if I use all the numbers, you're going to see my answer is going to be different, okay? So 523 times 1.077 blah 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 times 523. See how it's going to be somewhat off, okay? It's a little bit close, but if we all want to get the same answers, let's just stick to maybe the first two decimal spots, okay? So here, let's do another example. This is on the left side, okay? So a train is moving towards a sound detector at 31 meters per second, blows a 305 hertz whistle. What is the frequency detected on a stationary train? And what is, and on a train moving towards the first train at 21 meters per second. So let's do the first part. Ignore this last sentence, okay? We're going to do the first part. This is the easy part right here. 305. V is speed of sound, speed of sound. Okay. This is the velocity of whatever's making the sound. This is the velocity of what's listening to the sound. So one of these might be a 0 or they might not. Okay, so let's just read the problem again. So a train is moving towards a sound detector at 31 meters per second. So now we need to determine where do we plug this in? VD or VS? So the train is moving towards a sound detector. So the train is what's moving, right? So it's kind of like the last problem. So here you have the train and it's moving. And it's making the sound, right? So velocity of what's making the sound. The train is moving and it's making the sound that goes here. And it's moving to a sound detector. So this is, let's say this is the sound detector or you, and the sound detector is standing still, right? So it's not moving. Okay. So now let's solve. 343 minus 31. 312. The top was 343. 343 divided by 312. 343 divided by 312. Let's use, I'm not even going to round, okay? I'm just going to say 1.09. I'm going to multiply. 305 times 1.09. And that gives me my new frequency. Okay, that's the first part. Now the second part says, well, what if this sound detector wasn't standing still? What if it was also on a train and it was moving, going this way, right? So if this is the case, then everything stays the same. Speed of sound, speed of sound. We know that the train was going at 31 meters per second. And we're saying, well, what if this guy here was also in a train and it was moving this way? So we have the train making the sound detector, or maybe you going the other direction. So what's going to be the pitch, the new frequency, the pitch drop, right? So 343 minus 21, 343 minus 21, 322. 343 minus 31 is 312. 322 divided by 312, 1.03. I have to clear that out. 305 times 1.03. 314. It's going to be the new frequency. Okay, so now in this problem, we're gonna, let's go ahead and try to solve it. So a car is moving, so left side, your notes. A car is moving 26 meters per second, sounding off its horn at 360. Find the frequency it makes and use 343. So plug in the frequency, right? Frequency of the sound, 360. 343, 343. And the car is moving this fast and it's making the sound. So that goes, this is the velocity of whatever's making the sound. Right? And let's just say this one is 0, right? Okay. So here we have 343 minus 43 minus 26.8 gives me 316. It's 343. 343 divided by 316. 1.08. Let's clear that out. 360 times 1.08, and that gives me 388. Okay. Now there are some problems like this one. It says answer the above problem, but use the speed of sound in water. And you are not standing still, but moving at a speed of 2 meters per second. So let's say that everything is pretty much the same, 360. But this time, instead of 343 for the velocity, we're using the speed of sound in water. And if we check our notes, the speed of sound in water is 1484. You always use 343 unless the problem specifically tells you to use something else, okay? So everything's the same. So instead of this 0 here, it says, but you're moving at 2 meters per second, 2. And then this one is still 26.8, right? 26.8. So 1484 minus 2, 1482. Well, that was easy. I didn't need a calculator for that. Oh well, 1484 minus 26.8, 26.8, 1457. 1482 divided by 1457, 1.01. I'm going to do it up here. 1.01 times 360. That gives me 363 hertz. Okay. Okay, now I want you guys to notice that up to this point, all of the problems that we've been doing, we've been plugging in 0 here, right? Because this is the person listening to the sound. This is whatever's making the sound. Sometimes this bottom part could be 0. Okay? You just have to be careful. So the easiest way to go about this is, okay, this is the velocity of whatever's making the sound. Okay, is whatever making the sound moving, yes or no? And you know, you're gonna have to read the problem, and yes, up to this point they have all been doing that, right? Now if you look at this problem right here, you're an automobile traveling 25 meters per second towards a pole-mounted warning siren. If the siren's frequency is 365, find FD. So FD is the answer. So FS we know is 365. speed of sound, speed of sound. And let's look at the problem again. So this is the velocity of what's making the sound. So it says you are in an automobile traveling 25 meters per second towards a pole. The pole is what's making the sound, right? You're not making the sound, you're traveling that fast. The pole is making the sound. So there's the pole, it's making the sound, and this is you going towards it. How fast is the pole moving? Is it moving? It's not, right? Velocity of what's making the sound, this one is 0, okay? So I want you to notice, here we've been putting 0 on top, okay? With all these examples that we were doing. Okay, we were putting 0 on top, okay? That's because you were standing still and then the other object was moving. Velocity of what's making the sound. Here the car was making the sound, it was going that fast. In this example, the car was making the sound and it was going this fast, 26.8, that one goes here, that one, then this one was 0. But in this example, you're going this fast, but the pole is not moving, okay? The pole is 0, in this case 0 is on the bottom and 25 goes on top, okay? And from here, you guys can solve the rest, okay? Another thing is for here, 3.5 megahertz is 0.000035 hertz. So you're gonna have to use this for this part right here for FS. Okay, you guys can solve the rest. And the last thing that we're gonna go over is this part. So you're going to copy this on the right side. So the Doppler effect is an increase or decrease in the frequency of sound, light, or other waves as the source and observer move forward or away from each other. The effect causes the sudden change in pitch noticeable in a passing siren, as well as the redshift seen in astronomers. So in other words, as let's say there's a siren or an ambulance coming towards you, you're standing still, okay? And this is the sound that the ambulance is making, right? This is the sound wave coming towards you. But as it's moving towards you, notice the sound waves start getting smaller and smaller and smaller, okay? So that is going to change the sound, the pitch of it. That's going to change it, okay? Remember here, very, very big sound waves, that would be like thunder, right? And if you have really small ones, that would be like, let's say, a really high notes, right? And that's exactly what's happening here. You have the sound wave kind of changing from its original sound to maybe a different frequency, a different pitch, okay? And same thing, as it continues moving this way, the sound waves are going to get smaller and then they're going to start getting larger and the pitch is going to drop. Okay, so the best way to see that is with the video that I will play. But let's do a last little, there we go, right here. Okay, so here you have your waves, okay? And you can copy this, that's okay, wherever you have room on the left or right side. So here you have your sound wave, and this is just some terminology you have to kind of know. This is the amplitude, okay? This is the crest. The amplitude's how high up it goes. The higher the amplitude, the higher the energy the sound is gonna have, okay? So if it's a sound wave that goes kind of like that, like really, really high, then it's gonna have more energy, okay? So these are called transverse waves. And they're perpendicular to the direction of the wave. So these are transverse waves. These are called longitudinal waves. And here it kind of shows you how the sound waves travel. So let's pretend that these are like molecules. So anytime that here you have a person shouting, okay, the sound waves, the air molecules are going to kind of start crashing into each other, until they get to like your ear, okay, over here. So the sound moves forward and the oscillations move back and forth. They move parallel to the direction of the wave. Okay, so a best way for me to show this is by showing you that other video. Okay, and this is just another thing that you can copy anywhere on left or right side. That's okay, wherever you have room. So we need to go over interference of two waves. Passing through the same medium are called antinodes. So you're going to have different sounds and they're going to kind of interfere with each other. Those are called antinodes. So just terminology, okay? So 1, 2, 3, 4. So here you have one sound wave, two sound waves. Here you have another one, and so on, okay? Okay, so here you have 3 antinodes, okay? And here you have 2.